All right, welcome to page 4. Example 8, verify that the indicated function is an explicit solution of the given differential equation. Assume an appropriate interval I of definition for each solution. And so what we're going to do is we're given the differential equation over here on the left, and then we're given the indicated function, which we're told that this is a solution to our differential equation. And so what we're going to do is we're going to check to see if this is a solution. So all we need to do is we're just going to take the derivative of y, we're going to plug it into our differential equation and see if, our differential equation holds true. So let's go ahead and take the derivative of y here. So y prime is equal to derivative of 6 over 5 is just 0, minus 6 over 5 e to negative 20t. So we're going to go ahead and multiply negative 6 over 5 times negative 20. Negative 20 divided by 5 is 4, or negative 4. 4 times 6 is going to be 24. So we have 24 e to the negative 20t as our derivative. So there's our derivative, and here's a differential equation. We're going to go ahead and plug this into our differential equation and see if we actually have a solution to our differential equation. And so we're going to go ahead and plug in dy over dt is going to be 24 e to the negative 20t plus 20 times y. Y is 6 over 5 minus 6 over 5 e to the negative 20t, and that's supposed to equal 24. So I'm going to go ahead and distribute the 20. So I have 24 e to the negative 20t plus 24 minus 24 e to the negative 20t. And when I do the math there, that's just going to be 24. And so 24 equals 24, so that checks out. So we do have a solution. So this is a solution to our differential equation. And that's all we had to do. To start off, it's not too bad. We're just going to, check. All right, for the second one, example 9, we're going to verify that the indicated function is an explicit solution of the given first-order differential equation. And then we're going to proceed by considering phi simply as a function given its domain, then by considering phi as a solution of the differential equation, and give at least one interval of definition. So when we're looking at this, we're going to look at, okay, y is 1 over 4 minus x squared. We want to talk about the domain. Well, the domain of this is going to be where 4 minus x squared, so our domain is x, where 4 minus x squared is not allowed to equal 0. So that's our domain. That's really nice. Or what we can say is where x cannot equal two values. The two values would be positive 2 and negative 2. So you can't divide by 0. And so that's our domain of the function. All right. Now what we're going to do is we have our function y equals 1 over 4 minus x squared. Let's go ahead and see if this is a solution to our differential equation. We're going to take the derivative of y. So y prime is equal to, before I do that, let me get rid of this. I'm going to rewrite what y is. I'm going to say y is 1, and I'm going to say y is 4 minus x squared to the negative 1 power. It's easier for my differentiation. So that means that y prime is equal to negative 1 times 4 minus x squared to the negative 2 power times the derivative of the inside, which is going to be negative 2x. And so that just gives me, when I plug everything in, that's going to give me 2x over 4 minus x squared. All right, so there's my derivative. So we're going to go ahead and plug this into our derivative and see if it equals 2x times y squared. So we have 2x over 4 minus x squared equals, now we have 2x squared. Let's go ahead and plug. So we have 2x times y squared. Y is 1 over 4 minus x squared. And then hopefully you see that if I multiply the 2x there, it's going to equal the same thing, that they check out. All right. And so it says it wants to give us, we want to give at least one interval of definition. And so we know that this is now a solution to our differential equation. An interval of solution, you could say, is going to be -2 to +2. Again, open parentheses because we're not allowed to equal -2 and +2. You could have also said -infinity to -2. And you could have said, or you could have said 2 to infinity. Again, you had 3 possible intervals of definition. Again, that we're gonna look at that solution, or that potential solution, as just a function, and we're gonna find the domain, and that will help us find the interval of definition. All right, the last one that we're gonna take is example 10. We're going to verify that the indicated expression is an implicit solution of the given first order differential equation, and then find at least one explicit solution. All right. So the first thing that I want to do is I actually want to write this in terms of a differential equation. So again, our dependent variable is going to be y, so independent variable is x. So I'm going to multiply this entire equation by 1 over dx. I'm going to just multiply that whole thing by 1 over dx. So I'm just I'll put a parenthesis there so that you see that it's multiplication. So I'm going to multiply through. I'm going to get 2xy plus x squared minus y dy over dx equals 0. Again, if you just want to say y prime instead of dy over dx, go ahead. When I did this, I always just kept using y prime. But I just wrote it as dy dx. So here we have -2x squared y plus y squared equals 1. And we're going to verify that this implicit solution is a solution to our differential equation. And then we want to find one explicit solution, meaning we want to find a solution where we solved for y. All right, so that's fun. It's not too bad. So what we're going to do is we're going to go ahead and verify that this is a solution. So we're going to go ahead and take the derivative of this, and then we're going to use implicit differentiation. So I'm going to go ahead and take the derivative of this function with respect to x. So here's going to be a product rule, -2x squared y. So the derivative of -2x squared is going to be -4x times y plus the derivative of y, which is 1. So I'll say -2x squared, and because I took the derivative of y, I have to denote that we took the derivative of y, dy over dx. Plus, again, since y is the independent variable, when I take the derivative, I have to denote that we took the derivative of y, so dy over dx. Set that equal to 1. All right, now, again, we want all of our derivatives together, so I'm going to move that -4xy. I'm going to try to keep it in the format that we had over here. So we're going to try to keep it equal to 0. Oh, sorry, I forgot to take the derivative of the right-hand side, which is set equal to 0. So I'm just going to keep all my values that don't have that differential to the left so that we can see where this works out. All right, so I'm just going to go ahead and say -4xy. And then I'm going to bring in my derivatives together. So I'm going to go ahead and write this as negative plus -2x squared plus 2y dy over dx. And the only reason I'm keeping it in this format is so that I can keep it kind of how we have it written right here, where we have, the xy's on the left and then for the function for our derivative on the inside. Now notice, we have some negatives in our, in our implicit differentiation that we don't have in the original differential equation. So what I'm going to do is I'm going to pull out a negative. I'm going to pull out -2 because I noticed that, there's a factor scale of 2 there. So I'm going to pull out a -2 of the whole thing, and I'm just going to be left with 2xy plus, and then I'm going to change the inside here to be x squared minus y, because I pulled out a -2 from there, dy over dx. That equals 0. When I divide everything by -2, I'm just going to get 2xy plus x squared minus y dy over dx. So we're told, hey, this is a solution. All right, that's great. That's probably not very difficult for you because you're used to this. You're used to taking, you're used to doing implicit differentiation. The part that I guess now it makes it a little bit more complicated when we're talking about differential equations is now we want to express our implicit solution as an explicit solution. So we got to figure out, how can I write this as an equation of y equals? All right, so what we're going to do is I'm going to rewrite this. All right, I'm going to rewrite the implicit solution to be this: y squared minus 2x squared y minus 1 equals 0. What I'm going to do is, in order to write an equation for y, this is an actual quadratic equation in terms of y. And so what I can do is I can use the quadratic formula to solve for y, where a is 1, b is negative 2x squared, and c is negative 1. And so I'm going to say y is equal to negative b, so 2x squared, minus, negative b plus or minus the square root of b squared, so negative 2x squared is just going to be 4x to the 4th, minus 2 times 1 times negative 1, so that's going to be a negative 2, so plus 2. I'm sorry, minus 4ac, so plus 4, all of that over 2 times a, so 2. All right. And one thing that I notice here is that I can pull out a 4 here. When I pull out a 4, it's going to be a 2. So I'm just going to be left with x squared plus or minus the square root of x to the 4th plus 1. And so this right here, I have y. This is now an explicit solution. And it said you find at least 1. Here I found 2, all right? Where I would only have 2 because it's y squared. So there's 2 potential solutions. So I could either say y equals x plus the square root of x to the 4th plus 1, or y equals x squared minus the square root of x to the 4th plus 1. So I'm just going to keep that there. Again, all you got to do is find one. I just found both of them for you. All right, I'm just going to continue to go over the last page because it's real quick. That way I don't have to make a new video. So when we talk about families of solutions, when we solve a first-order differential equation, we usually obtain a solution containing a single arbitrary constant or parameter c, one parameter family of solutions, similar to when solving an nth-order differential equation and set equal to 0. We seek an n-parameter family of solutions. So a solution of a differential equation that is free of arbitrary parameters is called a particular solution. Sometimes a differential equation possesses a solution that is not a member of a family of solutions of the equation. Such extra solution is called a singular solution. An example of a singular solution would be a differential equation y prime is equal to xy to the 1/2. It possesses just one parameter family of solutions. Y equals 1/4 x squared plus c squared, where y equals 0 is a singular solution. So when I talk about families of solutions, you're used to seeing, that's why you have the plus c. If I ask you, hey, if I give you the, differential equation y prime equals 2x, all right, you would say, oh, then the original solution was just x squared plus c, where now that plus c gives you the family. So that when you look at it, that could have been the original equation, or this could have been the original equation. Well, that should have been right there, or that could have been, where your c is just going to change where it falls on the y-axis. And so that's what we talk about when we talk about a family of solutions. All right, that's it. Hopefully you enjoyed your first day of differential equations.